Welcome everyone. In this video, we'll go through part 3 of reinforcement learning. I am Vijay, applied scientist at Amazon. In the earlier course, we talked about the temporal difference learning and deep Q networks. And in this video, we'll talk about the policy gradient methods, actor critic methods, multi-agent RL with human feedback, challenges in RL frameworks and tools, and finally hands-on demo. So at first, we will start with policy gradient methods, which covers reinforced, log likelihood tree, and baselines. So why policy gradient methods? So let's first recall the value-based methods. The value-based reinforcement learning algorithms such as deep Q networks operate by first learning an action value function, which is defined as Q S comma A. And the policy itself is derived implicitly from these Q values by typically selecting the action with the highest estimated value, which is defined as or max of A. But the value-based methods has certain limitations. The first limitation is it only handles discrete actions. One major challenge arises when dealing with environments where the actions are continuous or the action space is huge. For example, controlling a robotic arm where the action might be precise torque to apply and joint. If the action space is continuous, performing this maximization step becomes a non-trivial optimization problem. One of the possible solution is discretize the action space, but results in loss of precision. And the second limitation is the learned policy derived from the Q function is typically deterministic. And the value-based methods struggle to learn the stochastic policies directly. That's where the policy gradient methods came into the picture, where the policy gradient methods offer a different path. Instead of learning values first, these methods directly learn the policy itself that maps states to the actions, which are defined as given the state yes, we'll apply the policy network to get the action probabilities defined as P A1 comma S A2 comma. That maps states to the probability over the action space. Or it can learn the distribution parameters defined as mu and sigma. By parametering the policy directly, we shift the optimization problem where we are no longer trying to actually estimate Q values. And policy gradient methods as well handle continuous action spaces more naturally by directly outputting the parameters for the probability distribution over actions, and it learns stochastic policies and with simpler action selection. And the policy network parameters, which are defined as theta, are calculated by maximizing the expected cumulative reward. So let's define J of theta. J of theta defines the objective function which represents the expected total discounted return by following the policy pi of A. And we are searching for the policy parameters theta that maximizes this objective function. So to train the policy network, the key requirement is the need of the derivative of the expected return, which is defined as J of theta. Once you have delta of J of theta, which is defined as the gradient of the objective function, the model parameters can be updated as given below. Taking derivative of the expected return usually requires differentiating through the unknown environment transition dynamics. That's where came into the policy gradient theorem that proves mathematically that gradient of the objective function, which is defined as delta of J of theta with respect to the policy parameters, is proportional to the discounted cumulative return multiplied by the gradient of the log policy. So how did we come up with the solution? So we will go through the step by step to get the above equation. The first step is let's define the objective function, which is defined as J of theta, which is integration of the probability of the trajectory and the expected cumulative return from by following the corresponding trajectory. In the second step, we will take the gradient of the objective function, which is defined as delta of J of theta. And we use the corresponding identity as shown below. And we will use this identity to come with the equation 3. So once you have after the equation 3, then again, we reconvert into the expectation form, which is defined in equation 4. In the fifth step, we expand the probability of the trajectories in the form of the transition in the states and action and the transition space. Once you get once you have the probability of the trajectory, we'll apply the log on the equation 5 to come up with the equation 6, which converts the multiplication into addition form. Then we take the gradient on the log of P of the probability of the trajectory, which is once you apply the gradient, the first and third term will vanish out and the second term only remains. And we will take the output of the seventh equation and we will substitute that into the equation 4 and we will get the corresponding gradient equation. The reinforced algorithm. The policy gradient theorem provides a way to calculate the gradient of the expected return with respect to the policymator. But to apply this theory, a practical approach is required to estimate and use this gradient. So that's where the reinforced algorithm came into the picture, which is already known as Monte Carlo policy gradient. The idea is we want to adjust the policy parameters theta such that actions leading to higher overall returns becomes more probable and actions leading to lower returns become less probable. Since we usually cannot compute the expectation, the reinforced algorithm uses the Monte Carlo estimation. So in the Monte Carlo estimation, we run the current policy to generate one or more complete episodes. And for each episode, we calculate the return, which is defined as R of t for each time step, and we approximate the gradient using the corresponding sample data. So let's go to the algorithm step by step. Initially, we start with randomly set policy with the parameters theta. And for each episode, we run the current policy. And for each time step t from 0 to t minus 1, we collect the trajectories defined as state, action, and reward, and we compute the return. Once we compute the return, we calculate the updated direction as shown in the C. And once we calculate the updated direction, we will update the parameters as shown in below, as shown here. So the idea is if RT is larger than positive, the update pushes theta significantly in the direction that makes action AT more likely in state yes. The algorithm reinforces this action because it leads to a good outcome. But if RT return is very large and negative, the update the update still pushes the theta in the direction indicated by the score function, but the magnitude is very small. It might even push from the direction if R is negative. So here we will see what are the strengths and weaknesses of the reinforced algorithm. The first strength is the simplicity. The core concept and update rules are relatively straightforward, as we discussed it in the previous slide, and direct optimization and value-based reinforced algorithms such as deep networks operate by first learning the action value function, then calculating the policy. But in the reinforced approach, we directly optimize the policy for the objective function. And the third one is a compatibility. Works naturally with both discrete and continuous action spaces, and it also learns stochastic policies. In addition to the strength, the reinforced has the certain weaknesses. The first one is the high variance. The Monte Carlo estimation of the return based upon the single trajectories can be extremely noisy, and different episodes can lead to significantly different returns. Even if the policy changes slightly, it results in high variance in the gradient estimation. The high variance makes learning unstable and slow. And the second weakness is sample inefficiency. It requires many episodes to converge because of the noisy gradient estimates. And third one is requires complete episodes. Updates are performed only after the episode finishes, which can be very problematic in very long or non-terminating task. So to here we will see the solutions for reducing the variance. So as we discussed in the previous slide, the reinforced algorithm suffers from high variance because it uses single sample trajectory to estimate the expected return. High variance in the gradient estimate has several negative consequences, which which are noisy and slow convergence, and the sample efficiency, as we discussed earlier. So what is the solution? So here the the solution is to subtract a baseline from the return. Let's define the baseline B of ST. Here we use the corresponding baseline to center the reward signal, making updates relative to an expected outcome so that the agent learns how better or worse an action performed. So instead of taking the return directly, we subtract it from the baseline. So baselines in policy gradients reduce gradient variance without introducing any bias. So we will see what are the different common baselines. So one of the baseline is the constant baseline, which is average reward. The average reward, which is simple and effective, but the main challenge is it doesn't adapt to the value of the specific states. The second baseline is state dependent baseline, which is one of the most common approach. So one of the key insight is subtracting baseline doesn't introduce any bias. And it was mathematically proved that the expected value of the baseline term evaluates to exactly 0. Next, we will discuss on the actor critic methods. Actor critic methods solve the biggest operational flaw of reinforce the requirement to wait for full episodic endings. It combines the policy-based and value-based, which are defined as actor and critic. The actor's role is to control how the agent behaves. It learns the parameterized policy denoted as pi A of S, and theta represents the policy network parameters. The goal is to adjust its parameters theta such that policy maximizes expected cumulative reward. The next is the critic, which is action evaluator. The critic role is to evaluate the actions taken by the actor. It learns the value function that estimates how good it is to be in certain state or how good a specific action taken in that state is. Think of critic as a component responsible for judging how good the actor's chosen action was. It outputs a scalar value representing the estimated return from the current state or the state action pair. The key advantages are of actor critic architecture over the reinforce is the updates are happening at every step, not at the end of the episode, and lower variance through bootstrapping. Bootstrapping replaces the long-term path randomness with smooth learned network estimates, which is coming from the critic network. Third advantage, stable training and sample efficiency. By combining the strength of policy optimization with the value function, we get the stability of bootstrapping without losing the flexibility of direct policy optimization. As you can see here, the actor alone, which has the high variance, which is pure policy gradient, critic alone, which can't handle continuous actions easily. But combining the both, we can have the lower variance with flexible policy. Sample efficiency and drastically reduce the volume of action environment interaction data needed to arrive at an optimized policy. Let's see the loop. So at the given an environment at a particular state, yes, the actor takes the corresponding action based by following the particular policy pi. And the environment provides the reward, and the next state, the critic computes, estimates the value of the action taken by the actor, and it computes the temporal difference error, the advantage as in feedback to the actor. The actor takes that feedback and updates the policy network parameters. The next is advantage actor critic. Advantage actor critic is a specific and popular implementation within general actor critic framework, where actor learns the policy and critic learns the value function. The advantage function stabilizes the learning using the advantage function as the critic instead of action value function. The idea is that advantage function calculates the relative advantage of taking an action compared to the other possible actions at a given state. Yes. If advantage is greater than 0, then the gradient is pushed in that direction. If advantage is less than 0, then the gradient is pushed in the opposite direction. But the problem with the corresponding, the first equation is it requires two value functions, which is qs comma a and v of s. So here we approximate the q with the td, the temporal difference, which is given in the second equation. So the advantage in the second equation is given by the immediate reward, which is r of t, and the discounted value of with discounted estimated value in the next state. Once we define the advantage function, then we will discuss about the actor update. So the actor's parameters theta are updated using the policy gradient approach, but scaled by the advantage function derived, which is derived from the critic here. So here we will define the loss function for the actor. Then we will define the update rule based upon the loss function. So once we combine both 1 and 2, we will get the third equation, which is the update equation for the policy network parameters. The next is the critic update. The critic parameters, which is denoted as phi, are updated to minimize the difference between the value estimate of the critic network and the target value, which is denoted as GT. The GT, which is typically denoted as the TD, the temporal difference target, which is the reward at time t and the discounted estimated value of the next state. The loss function for the critic is typically the mean square error loss. You can see it here. So once we define the loss function, we will define the update rule. Once you combine the both, then we will get the update rule for the critic. A common implementation pattern for the advantage actor critic involves the neural network architecture, where initial layers are shared between actor and critic and followed by a separate output heads for each of them. Advantage actor critic provides a solid framework by using the advantage function to guide the policy updates. But its synchronous nature can sometimes be a bottleneck. Generally, in advantage actor critic, which is A2C, are typically collected from batch of experiences gathered by multiple actors running in parallel, then applied to update the central model. The synchronization step can limit throughput, especially if some actors are slower than others. So that's where the asynchronous advantage actor critic came into the picture. It has the global network, which is a central global network containing the parameters for actor and the critic that all agents will ultimately contribute to improving. Then we have the worker agents, where multiple workers are created and each with local copy of the global network. A local copy of the actor and critic initially synchronized with the global network parameters. The next, how does the workers approach? So each worker interacts independently with its copy of the environment to collect the experience here. Next, we'll compute the local gradients. Using the collected experiences, each worker calculates the gradients for both its local actor network and its local critic network. Next, we have the update global, which is the asynchronous update. Once a worker computes its gradients, it sends them directly to update the global network parameters. This update happens asynchronously, meaning that the workers doesn't wait for other workers. It sends out its update and immediately resets its local network parameters to match the global parameters. Then continue interacting with the environment to collect the experiences. So why asynchronous works? The first is the decorrelated experiences. Because each worker interacts with its own environment instance using the different version of the policy. So this inherent diversity acts similar to the experience replay buffer. And faster wall clock training on the multi-core CPUs because of the synchronous nature. And the third advantage is natural exploration through diverse worker experiences. And the last, the A3C largely superseded by advantage to critic plus GPU parallelism. While A3C introduces the powerful asynchronous update scheme, but A2C is often simpler to implement and can be more efficient when using GPUs effectively. A2C typically batches experience from multiple parallel actors and perform a single larger update. This patching can leverage GPU parallelism more effectively than the asynchronous update of A3C. The next we will discuss about the generalized advantage estimation, which is designed to reduce variance in policy gradient estimates while balancing bias. So which bridges the bias and variance trade-off. So how does it works? So first, let's see what is the problem. The one step, the temporal difference. It has low variance and high bias. But in the multi-kernel approach, which is coming from the reinforce, which has zero bias and high variance. So these are the extreme two steps which having low variance, high bias, and high variance and low bias. So that's where the generalized advantage estimation came into the picture. So you can see the below equation. So here the gamma represent the discount factor and lambda represent the exponential weight discount. And the lambda controls the bias variance trade-off and the delta represents the temporal difference error, which is the TD error. So let's see how by varying the lambda, how does the bias and variance trade-off happens. So if we take lambda equals to 0, then this equation ultimately collapses into one step, the temporal difference, which is low variance and high bias, which is same as actor to critic. And lambda equals to 1 will collapse into Monte Carlo, which is high variance and zero bias, which is same as the reinforce. And any value between 0 and which balance the two, which is the bias and variance, and achieving a sweet spot for the stable and rapid policy improvement. Next, we will discuss on the multi-agent RL. So everything we covered so far, policy gradient, actor critic has been single agent, where one agent, one environment, one policy. But the real world is multi-agent. For example, warehouse, which have hundreds of robots. So when multi-agents learn simultaneously in the same environment, fundamentally new challenges emerge that breaks the assumption of single agent RL. And in multi-agent RL, all agents are part of your environment and they keep changing as they learn. So this means the environment is non-stationary from each agent's perspective. So given that in a multi-agent system, agents interacts with other agents and we have different types of environments. So one is cooperative environment where agents need to maximize the common benefits. For example, in a warehouse, robots must collaborate to load and unload the packages efficiently. And second one is competitive. In this case, your agents wants to maximize its benefit by minimizing the opponents. And third one is the self-link. So let's discuss each of them in the next slide. In cooperative approach, all agents shared a single team reward. Think of warehouse with 100 robots and they all get the same reward based upon the total packages delivered. The challenge here is the coordination and credit assignment. So centralized training, decentralized execution is one of the approach. The practical approach during training, the algorithm give access to everything like observations, all actions, the complete global state. So this makes the learning much easier because you can properly assign the credit. Where the QMix and MAPO are some of the cooperative multi-agent RL approaches. And in competitive settings, we simply let each agent run its own RL approach and treat other agents as part of your environment. Each agent tries to maximize its own reward and agents compete against each other. Each agent optimizes its own objective. In zero-sum games, maximize your reward inherently means minimizing the opponents. So this connects to the classical game theory, which is finding Nash equilibrium and minimax strategies. And third part is the self-play. The self-play is a powerful idea. Instead of needing a separate opponent, the agent plays against copies of itself. The opponent is the agent's current policy. So the agent improves, its opponent automatically improves too. The difficulty scales perfectly with the agent's skill level. So this creates which we call an auto curriculum. The agent never faces an opponent that's too easy or too hard. It's always facing a challenge at exactly its level. The agent generates its own training data through self-play, which drives policy improvement, which makes the self-play harder and which drives more improvement, which is a virtual cycle that terminates at super human level. Next, we will discuss on the RL with human feedback. The language models which are trained the raw internet can generate fluent text, but may produce harmful, unhelpful, or misaligned outputs. So aligning the language model to follow the complex human values is one of the main requirement. So here RL with human feedback, which is the training paradigm that aligns AI systems with human preferences by using human feedback as the reward signal. So let's discuss what is the problem. So here specifying the human concept, like for example, politeness, helpfulness, it's very hard. Here defining the reward function for this politeness and helpfulness, it's very interactable. So the solution is to learn reward from the human preferences. So human can easily compare two outputs and say which is better, even they can't write an explicit formula. So RLHF bridges this gap. Learn what humans prefer from comparisons and then optimize for it. Instead of defining the handcrafted reward function, RLHF learns a reward model from the human preference or comparisons and then optimize the policy using reinforcement learning against the learned reward. So there are 5 stages of the pipeline, which is pre-train, train the language model on the large text corpus, and supervised fine-tuning on curated demonstrations. Then next, collect the preferences, generate pairs from supervised fine-tuning and human label preferences. The fourth step is the train reward model. Once you have the collected preferences, train the reward model and the preference data via Bradley-Terry laws. The fifth step is the RL fine-tuning, which is optimize LLM with the PPO using the reward plus scale penalty. So let's discuss about the reward model. So here thousands of human labels provide preference data. For example, let's given the prompt and the response A and the response B and what is the preferences. The humans can provide the how good the two responses, response A and the response, and pick which is better. So the reward model predicts the scores for which is defined as R of the response A and the response B. Then we apply the Bradley-Terry model to give us the probability of comparison, which is the probability of A greater than B. Then we define the loss function that maximizes the likelihood of the human preferences. So this pushes the reward model to give higher scores to human preferred responses. The next one is the PPO fine tuning. Once you have the reward model, the learned reward model for the reward model score for the generated responses, which is defined as R of the model given the response. Then we add the hyperparameter controlling the strength of the KL penalty. The KL penalty is which prevents diverging too far from the pre-trained behavior. So we add the KL penalty in addition to the reward model. So which act as the rubber band connecting with back to the supervised fine tuning. The next, the beyond the RLHF. So there are multiple approaches beyond the RLHF, which is the direct preference optimization that skips the reward model, which directly optimizes the policy from preferences. And the next is using AI as a feedback instead of human feedback. And the other one is the constitutional AI, which have the self-critique and revision. And there are other approaches which can reduce annotation cost while maintaining the alignment with the human preferences. So next we will discuss the challenges in RL. There are multiple core challenges in RL. The first one is the sample efficiency. So RL agents are incredibly data hungry. The goal of ability of RL agent to learn effective policies with minimum interactions is with the environment. So there are multiple approaches which can mitigate the requirement of millions of interactions. So instead of interaction with the real environment, we can learn a model of the environment, which is model-based RL, and offline RL, which learn from the fixed data set of past interactions, and there no new environment interactions are needed. The third one is pre-train on similar task, which is the transfer learning, then fine-tune on the target task. The next challenge is the reward shaping. The reward function is where you encode what you want the agent to do. So if they have the reward function wrong, then the agent will do what exactly the same thing. So the first approach to designing reward function is one of the critical challenges. So the solutions to mitigate the designing the good reward functions are, instead of you writing the reward function, let it by watching an expert, which is inverse RL and RL with human feedback, which we discussed it earlier, and the reward decomposition, which breaks the complex reward into simpler components. The next one is the sparse rewards. The agents typically rarely gets feedback signal. So imagine learning to play chess where the agent only gives the agent only gets feedback at the very end. All right. So given the agent an internal reward for visiting novel states. So to avoid the issues, the mitigations are like curiosity-driven exploration and hindsight experience replay. And the challenge is the stability. Deep oral training is notoriously unstable, which makes the training oscillates and diverges. To overcome the issues, the challenges, the mitigations are use the target networks, maintain the separate target network that updates slowly, and the gradient clipping. If the gradient gets too large, clip them to the maximum value, and PPO clipping, the limit how much the policy can change in a single update. The fourth challenge is exploration versus exploitation. The exploration is which is trying new things. Exploitation is using the known strategies. So in RL, the too much exploration makes slow convergence, and too much exploitation stuck in local optima. So balancing both is one of the critical challenge. Credit assignment. So which action in a long sequence costs the reward? right? So let's take, for example, you win a chess game after 40 moves, but which moves were brilliant and which were mistakes? But the reward comes at the end, but the decisions were made throughout. So the credit assignment, like which move is good or bad, is one of the critical challenge. And the next challenge is the similar to real transfer. The training in simulators are very fast, cheap, and safe, but policies trained in simulation fails in real world. So the possible solutions are domain randomization. So here randomize the simulated environment. And second approach is system identification, where carefully measure and calibrate your simulator to match reality as close as possible. The other challenge is safety and constraints. The how to explore the safe RL. All right. So for example, a self-driving car can't explore running, seeing the left side to see what happens. So we need the conservative policy optimizations. So where only update if you are confident the new policy is safe. And the last challenge is the reproducibility. So high variance across seeds and sensitive to hyperparam. This is one of the critical challenge here. So run the same algorithm with the same hyperparam but different random seeds, and you may get widely different results. This makes RL research and development very painful. So next we will discuss about the RL frameworks and tools. There are multiple popular frameworks which were which can be used based upon the requirement. So for example, if you see the gymnasium, which is especially for single agent environments, and the petting zoo, the multi-agent, the framework environment. So similarly, there are multiple the popular RL frameworks which can be used based upon the requirement. So you can choose the right tool. For example, let's take learning or research. You can use the clean RL. For the production scale, you can use the RL lib. And for LLM fine tuning, you can use the TRL plus transformers plus the parameter efficient fine tuning. And different environments, you can use the gymnasium, petting zoo, or the Mujoko. So you can see the hands-on demo. So this is one of the demo setup. The environment is the card pool. And library we use is a stable baseline 3. The goal is to train an agent from the scratch and watch it to learn. So here we'll apply the two algorithms, which is deep Q networks, which is value based, and PPO, which is a policy gradient based. So here we can see the training curves, how the reward increases over time for the PPO and the deep Q networks, and agent BF from random to balanced pool. So here uh, the cart moves along the frictionless track with the pole hinged on the top. The agents must keep the pole balanced. So each time step, the pole stays upright, you will get the positive reward. Here you can see the settings of the deep Q networks and the proximal policy optimization. And this is the demo code. And if you can see the training progress, the training curves for the deep Q networks and proximal policy optimization. Here you can see that the deep Q networks have the very low average reward, whereas the PPO, which converts to the maximum reward. And here you can see the final performance comparison, the average reward across the 10 episodes for deep Q networks and the proximal policy optimization. And this is episode rollout for the 500 steps. And this is the how much is the pole angle is deviating. So here you can see the deep Q networks where the pole angle was going beyond the bounds, whereas the PPO, you can see the pole angles remain stable across the different steps. Let's recap the key takeaways. The policy gradient unlocks what value-based methods cannot. As we discussed, so it can handle the continuous action spaces or the action spaces very lot. The policy gradient methods were really one of the key advantage. And actor critic, which is the backbone of the modern RL. And the third one is the multi-agent RL extends to extend the extend the reinforcement learning to real world complexity. And the fourth one is RL has the significant practical challenges.